And all the lectures which is taking place here at the JLN Stadium is simultaneously broadcast to all the locations. Professor Indumathi is a particle physicist, and she is a professor of Institute of Mathematical Sciences, Chennai. She has been an active member of the India Neutrino Observatory project since its inception. Professor Indumathi's primary research interest is high energy physics phenomenology. Research interest of Professor Indumathi include work on atmospheric and solar neutrinos, nucleon, and nuclear structure functions. She has authored several research papers. Her topic today is a quest to understand the fundamental nature of the universe. May I request our director, Dr. Nakul Parashar, to come on stage and welcome Professor Indumathi with a flower bouquet. Thank you. So as we said that already there are many people eagerly waiting to listen to Professor Indumathi. Without wasting a time, I think we should start. Let the other people may join us. We'll request Professor Indumathi to start her presentation on a quest to understand the fundamental nature of the universe. Yeah, ma'am, the stage is yours.
Yeah, thank you so much. Yeah, I think I would like to move it out. So it's a great pleasure to be here. I thank the organizers for inviting me to give this talk. I'm not sure how this talk is going to work out because it was very difficult to imagine the audience. I've kind of split it up into two parts. A little very small portion where I talk about the basic science that is involved because after all I'm a physicist and that's really my main interest. But really in this talk, in fact, I really loved your posters over here. If you just look and see on both sides, these words, experimenting, discovering, achieving, and in fact, the order in which you say it matters. And you can think of reshuffling these words. And I think at the heart of what I want to talk about, the projects that I want to showcase, really the main thing that I want to highlight for you today are two things really. And in fact, if I succeed in that, I'll be very happy. One is to showcase these mega science projects, to tell you what it is that is driving science, basic science across the world today, of which India is also a part. India has many such mega science projects lined up. And the other is really to tell you about, and this is something which is more important for me really, and I think for Vigyan Prasar as a part of your science communication program, to highlight how deeply intertwined science and technology are in today's world. And that without progress in fundamental sciences, you will not be able to make corresponding strides in technology. So this is something I want to highlight. I think it gets lost sometimes because all children today have cell phones. They're very comfortable with technology, but they hate the science. So I want to try to, make you look at the science and the associated technology with a little different vision. I have left my pointer. Sorry, one moment. This is a short overview. As I said, I'll start with a little bit of a physics introduction. But really what I want to, is this clear? I have a feeling I should have put a black background. I didn't realize it will be so sunny, but yeah. I think the pointer will not be visible. I can just walk up. So as I said, I am just going to showcase 4 mega science projects. There are many actually coming up in the next 25 years in India. And as was said, I'm a part of this project, the India-based Neutrino Observatory, for a long time. So I will spend a little more time on it. But really, I will just give you a little flavor of 3 other projects. And I hope that it'll, especially among the students, it'll excite you enough that you go back and read about it. and especially for the young master's students, that you will actually want to go back and become a part of these projects which are actually coming up now. And then I want to make a couple of remarks when I finish talking about this. So I'm going to start about, at the very basic level, what do we mean by an understanding of the basic science that, through which we understand our universe today. So here is a very basic beginning. We look at matter. So I'm standing on a stage that is made up of matter. And matter, we know, is made up of, in fact, very smart students will tell you there are 4 states, not just solid, liquid, and gas, but also plasma. And in fact, plasma is one of the things that we will be looking at in one of the projects that I'll be talking about later. So while matter is made up or could be either one of 3 things, light, on the other hand, is made up of waves. We've heard about light being made up of waves. It has a wave nature, and that was something that we've been knowing since the late 19th century, when Maxwell actually made this discovery or told us about it. So when we talk about wave nature, and it's something that is at the heart of a lot of the science, or what we call quantum physics that we talk about today. So what is actually a wave? So waves you have seen, I mean, I come from Chennai. All children have been to the beach and have seen the waves. But mathematically, when we look at a wave, we associate 2 properties with it. So when I ask how this wave is doing in space, so I have, as I said, the pointer is not visible, it's too bright. So the first axis is the x-axis, it's a spatial axis. So if you look at the distance between 2 maxima or 2 minima of the wave, that distance is called its wavelength. So that characterizes the wave. And if you look at its evolution in time, which is here, not in space, but in time, it's a completely different coordinate. We should always keep that in mind. Then the distance between 2 maxima or 2 minima is called the time period. Its inverse is called the frequency. So this frequency, I have given the name nu. Okay, and there's a very special property that the product of the frequency and the wavelength actually defines the velocity of this wave. So this is the amount that you should know. So this is what we have about a wave, and a special notation given to the wave that is light, because it has a special velocity or speed called c. It has a notion c in vacuum or in air, which is practically the same thing. Light travels at this velocity, which is about 300 million meters per second, but its number, for those who are curious, you could ask, how is it that we know this number so exactly? And there's a very nice story over there. I'll leave you to find it out. Okay, so one main thing about these waves, and that also is something that you can observe, that waves actually go through each other. So when waves overlap, they can add so that the wave size becomes bigger. Those of you who experience wave made the second wave so disastrous when it hit in the east coast of Tamil Nadu, and also when if the waves are actually in such a way that the maximum of one coincides with the minimum of the other, then they can actually destroy each other. So they can become kind of zero. So this is called interference between waves, and this is a well understood phenomenon of waves. So this is what we think of light as. We think of light as a wave which has these properties. थोड़ा नीचे कर सकते हैं इसे जी, सुनिए, इसे थोड़ा नीचे कर दीजिए, ठीक नहीं है. So coming back to electromagnetic wave, so there are so many kinds of waves, okay, and these kinds of, okay, not worry about the title. I think he's got an offset somewhere. So I've just given you examples of waves. So depending on wavelength, you can see being very large to being very small. You can see that these wavelengths correspond to the wavelengths for TVs, mobiles, microwaves, human beings, remote, that is infrared, here, this one, X-ray, nuclear radiation, all the way across the scale, from large wavelength to small wavelength, or inversely from small frequency to large frequency, because you can see the product is a constant, right? So this form of energy as it travels, not just light, but similar waves in general, are called radiation. So for the common man, usually when you think of radiation, you think of nuclear radiation. You say, oh my God, there's radiation here, in Chernobyl. But radiation can be of all kinds. So there's electromagnetic radiation, there's particle radiation, which is like nuclear radiation, which could be neutrons or alpha, beta, gamma rays. There's acoustic radiation. You're hearing me through a combination of both sound and light, actually, because of electromagnetic waves. So there's acoustic radiation. In the sun also, there is acoustic transport of material. Okay, so the sun actually makes a sound. So, fancy things like that happen. And finally, there is gravitational radiation. And this gravitational radiation is something very interesting that one of the experiments I'm going to talk about has probed, and I'll talk about it in more detail later. ये ठीक नहीं हुआ? आधे में है, नहीं तो लैपटॉप मुझे दे दीजिए ना, मैं संभाल लूंगी. थैंक यू. आएगा? थोड़ा बड़ा कर दीजिए उसे. नहीं होगा? हो गया? थैंक यू. अभी उसको निकाल दिया आपने? सब है तो ये काम नहीं कर रहा है. ठीक है, पेज डाउन लीजिए, पेज डाउन कीजिए. ओके, वी विल ट्राई टू सी. पेज अप कीजिए. हाँ, नहीं, और ऊपर जाइए, ऊपर जाइए. सॉरी, हाँ, थोड़ा सा एक नेक्स्ट पेज आइए. नहीं, नीचे नीचे और नीचे. हाँ, बस बस. थैंक यू. Sorry about that. So we talked till now about light as a wave. But what was found in the previous century was that light also behaves like a particle. So you think of a particle intuitively, some people think of an electron, for example, as a particle. And light actually behaves also like a particle. And when it behaves as a particle, its particle nature is called a photon. So you might have heard of photons. They're actually a light quantum. So the light quantum is called a photon, and that's what brings us to quantum physics. And this discovery, in fact, that light can also be a particle led to the birth of quantum theory. So light can be either a wave or a particle. In fact, it's said to have a dual nature. And when you go back and look at an electron, you find that not only electrons, but all other particles that we know about also have a dual nature. That means that what you thought of as a particle also has a wave nature. And it has a very peculiar type of wave nature because you see that its wavelength, unlike that of a wave, is related inversely to its momentum. So if the momentum is zero, then of course there is no wave-like nature anymore because the wavelength goes to infinity. So when a particle is moving, it has a wave nature. But even if it's moving very slowly, it is acting like a wave. So what is this distinction then between matter and radiation? Because radiation can behave both like wave and particle, and particles or matter can behave like both particle and radiation. So there is actually no difference at some fundamental level between them. They both have a dual nature. This understanding that they both have a dual nature is what led to this quantum theory of physics. Why physics, quantum theory appears everywhere in chemistry as well. The quantum theory of science. Okay. So there's one very important consequence of this quantum physics, which many of you have seen in school in chemistry, in fact, which was called Pauli blocking or Pauli exclusion principle, where you say that two electrons cannot fill the same energy level, right? And this is something that translates in a little different language because you can see that the wavelength was inversely proportional to the momentum. You can see that when the wavelength is large, the momentum is small and vice versa, which means that if the object you're probing is very big, then the momentum or the energy associated with it is very small. That means the energy associated with some event, object, or activity is inversely proportional to the distance. So this is very important because we know that atomic sizes are about 100,000 times larger than nuclear sizes. The nucleus is a very, very small, compact object sitting in the middle of the atom. It's 100,000 times smaller than an atom. For those of you who know, one is in angstrom, the other is in Fermi units. And so because it's 10 power 5 times smaller, energies associated with any nuclear changes will be 10 power 5 times larger than the energy associated with electronic transitions. So this is something very important to keep in mind. It immediately answers the question, why is nuclear energy coming from such small amounts of material, whereas energy which comes from coal burning or oil burning requires such large amounts of material? Okay, because gram per gram, you get 10 power 5 times more energy from nuclear sources. Okay. So where does this energy come from? So it was Aston who found, almost exactly 100 years ago, he found a very simple thing. Hydrogen atoms are protons. Helium atoms have 2 protons and 2 neutrons. And neutrons are slightly heavier than protons. So you would actually expect helium to be heavier than 4 protons, but it turns out it's lighter. And it's lighter because of this binding energy. And the simplest way to understand binding energy is all of us have learned in school about ionization. If I take a hydrogen atom and remove its electron, then I get a charged hydrogen atom, right? Because the electron has been removed. But to remove the electron prefers to stay with its positively charged proton partner because that's what makes it stable, the atom. If you want to take it away, you have to give it energy. That is the binding energy. The same thing happens for when you have so many nucleons, protons and neutrons bound into nuclei. You have binding energy. So this little bits of energy all add up and give you the enormous amounts of energy that you see, say, for example, in nuclear reactors, or in fact, I will showcase in the sun, which actually is driven, the sun's energy is driven by nuclear fusion processes in its core. So, of course, I have one last slide to show. How can Einstein be left behind? Everyone knows E is equal to mc squared, though they may not know what it stands for. Now, what we understand is that for every particle, which is, for example, an electron, we have a corresponding antiparticle. So, if the electron has negative charge, the positron has positive charge and has exactly the same mass. And when a positron and an electron come together, they collide at rest. You can just have to imagine it. Then the total energy of those 2 particles is converted into pure photon energy. And that energy equivalent is twice mc squared. So mc squared from each of them, which means that if I have a particle with mass m, mc squared is the mass equivalent energy that I can extract by destroying it completely. So that is the meaning of this E equal to mc squared. And I'm not reading all the technical notes. For those who want to look at them, it's a little more advanced level. It really doesn't matter for the purpose of this talk. So I have now introduced particle, antiparticle. I have introduced notions of size versus energy. So now that I have given example of electron and proton, what are the kinds of particles that we have in this universe? What is the world made of at the fundamental level? And we lost the title, it's okay. But there are 4 fundamental forces in nature. I think everyone has learned about gravity in school. So we've all understood, yeah. Can take off my mask, is it okay? Fine, thank you. Yeah. No, the breathlessness is a remnant of COVID, getting COVID twice. that won't go away that easily, sorry, yeah. Yeah, but it makes it easier without the mask, thank you. So here, so there are 4 forces in nature. The gravitational force, we all understand. So 2 masses are attracted to each other. In fact, not just mass, we know that mass is equivalent to energy, right? So even if you have bundles of energy, they will be attracted to each other by the forces of gravity. And then there are the electromagnetic forces, which are like charges of electron and proton. So we know about them also. And the 2 new forces are called strong and weak interaction at the top of the second line in the thing. So the strong and weak forces are something new to us. They were learned about much later. The strong forces are what keep the protons and neutrons together inside the nucleus. Just think about it. We know that like charges repel. So how do you squeeze so many positively charged protons inside the nucleus? They should all be flying apart. So the fact that they actually stay together is because of the strong interaction, which is attractive at those short scale distances and overcomes the repulsive electromagnetic repulsion. And the weak forces, almost every particle in nature, in fact, I think every particle in nature experiences the weak interaction, and they are best described by looking at fusion processes that power the sun. Nuclear decays are another object. For example, in any fission reactor, you will find weak interactions and stuff like that. So physicists like to classify, all physicists like to classify, and the only thing I want to say is that there are therefore types of particles. For example, you're familiar, if you look at the particle listing in the table, proton, neutron, and electron are familiar particles to us. And you can see that the proton has every type of interaction, whereas the electron does not sit inside the nucleus, so it does not have the strong interaction. And the last particle is new to us, maybe, and that is the neutrino. The Indian Neutrino Observatory actually is going to probe this particle. It is a partner of the electron, as you can see over here. Okay, so this is associated with the electron is this particle called the neutrino. It is practically massless. It has no charge. And in fact, there's a very incredible thing that was discovered. There are copies of these things. It's just like, you take Xerox copies to be, sure that you don't lose your Aadhaar card, okay? But these are not exact Xerox copies. These are little heavier. The second generation is a little heavier than the first, and the third is even heavier. Okay, and we don't know whether there's a fourth one. We don't know why these generations exist, but otherwise they are practically the electron. This is called the muon. This is called the tau. Are all copies, heavier copies of each other, and otherwise have very similar properties. Just like we have the leptons, it turns out that the protons and neutrons which sit inside the nucleus are not point particles. They're not fundamental particles. Just like we thought an atom was indivisible and found the nucleus inside it, and then we found that inside the nucleus were protons and neutrons, we find that inside these protons and neutrons are the quarks. And these quarks have funny names. All you need to do is to remember that these are called the up-type quarks, and these are called the down-type quarks. Very easy to remember them. And they have exactly the same structure as these objects, which are the electron partners, which are called leptons. So now the question really is that now we don't know anything further than this. We don't know if these quarks and electrons are made up of further substructure. So the present research that is going on is actually to probe the properties of these particles. So now I'm going to come to the main part of the talk. I've just given this background. So we know our particle world. These are our particles. Still, there are some more particles. I have left them out, but for those who are curious, these are the force carriers. So just like we have photons, there are some more particles. So you can look those up as well. And I will only talk about this much because already this is complex enough, so I don't want to take it further. So I think we're going to again lose part of the top. Okay. I don't know what to do about this. Suni, ये दोबारा ठीक नहीं है? No, it's correct. The size of the screen is correct. He does not have it in slideshow mode. Could you help him with that? I'm really sorry about this. So I'm starting the first experiment. So this is, as I said, I will showcase 4 mega science projects which are coming up, ongoing, of which India is a part. And the first one is called FAIR. You cannot see the top. FAIR is a facility for anti-proton and ion research. So here comes the anti-proton. So just like we had electron and positron, the anti-proton is the antiparticle proton. And you can see that there is this huge structure. The ones in blue are already constructed. They're older parts of the machine which are there in, thank you very much. Yeah, I'm sorry to keep troubling you about this. So the blue parts are already there, and the red is what is being built right now. And various components of these accelerator are also being built in India. There's a very large participation from India, as you can see. You can large parts of Europe, Russia, and England and India are part of this collaboration, the FAIR collaboration. And the idea is to look at antiprotons or even new atomic nuclei, or as the name says, So what is it that the FAIR is going to do? So this FAIR is हाँ ऐसे ही छोड़ दीजिए बिल्कुल perfect. Okay, so here are the physics goals, which were promised and not seen. So the first question is that, although I told you that protons and neutrons are made up of fundamental objects called quarks, and I showed you that there are 6 quarks in nature, not all these quarks go into making these protons, and also these quarks cannot be seen individually. I cannot catch hold of a U quark and say, here's my U quark. So how do I believe that these quarks exist? So how do I know, or how do I guarantee or show these protons? One of these things studied is actually, why do we not observe these individual quarks? Why do we actually see aggregates of these quarks, which are called proton or pion or any other barrier that you might have heard of? Then next question is actually very interesting. What is the origin of the Hadron mass? So those of you, because I think all of you are interested in science and technology, because here you are at the science fair. So you must have heard about 10 years ago of the God particle. It was called the God particle, properly called the Higgs boson. And everybody in the media said that the Higgs boson gives masses to all particles. Well, that is true and not true. It gives masses to the fundamental particles. So it gives masses to the quarks, to the electrons. It gives masses to what we call the fundamental substructure of which all the other particles are made. But certainly it doesn't account for the mass of the proton. So it can account for the mass of the U and D quarks, which are in some units 2 or 3. But in the same units, the proton mass is 1,000. So how do you go from a collection of objects, some 2 or 3 objects which are mass 2 or 3 in, as I said, some units called million electron volts, to 1,000 million electron volts? There must be something there to bridge the gap. So this is something which is an open question today. Nobody understands it. And this is a very important aspect of the research that will go on in FAIR. What is the origin of the elements? This is something very important. I will talk about in the very last slide of my talk. Stuff like what is the structure of neutron stars? Does matter differ from antimatter? So these are the questions that are going to be probed at FAIR. But what I would really like to highlight for you, and I want this to be a recurring theme of my talk, that these massive projects bring with them their own technology. And I want to here distinguish between using technology and driving technology. Even if I pick up a pencil as a writer and I write, I'm using technology. But the kind of projects that I'm going to talk about here, that I am talking about here, actually are going to drive the progress in technology, because they are at the cutting edge of the present technology that is available today. And in fact, there's a lot of R&D going on in the technology to break even more frontiers. So the kind of technology that is needed, for example, this is a ring, as you saw in the earlier slide, where the antiprotons or ions are going to be accelerated, and the ring is going to be at a very, very cold minus 269 degrees using liquid helium. That is such a big challenge. Also, if you go to accelerate antiprotons in the ring, suppose I have air molecules. The protons are going to annihilate with the protons of the air molecules are going to annihilate with these antiprotons, and that will be the end of your antiproton beam, right? So you must have a very, very high vacuum, which is 10 power minus 15 times less than atmospheric pressure. So these are the technological challenges. And to achieve this, there's a lot of R&D going on, so that this project is not just driven by scientists, but by a whole lot of engineers who try to achieve these aims. So this is a project that is ongoing. It's planned to be commissioned in 2025. So here is some of the contributions of the Indian group, which is a part of FAIR. I don't want to go into what exactly these details are, just to highlight that there is a very large Indian presence. So there is, again, a lot of details over here, which I'm not going to go over. So this is one of the projects that is going on. The next project I want to talk about is a very interesting project which got the Nobel Prize recently. So you must have heard about it, called LIGO. LIGO is a laser interferometer gravitational wave observatory. First thing to remember is that though it's called laser, it's completely blind to electromagnetic radiation. The challenge was to make it that way. You don't want this instrument to see any electromagnetic radiation. You want it to see only gravitational radiation. That's because Einstein predicted that there will be gravitational waves, and people had seen it. In fact, Nobel Prizes had been given for indirect observations of these gravitational waves. But this experiment, for the first time, actually succeeded in seeing these waves. Incredible thing about it. So what they did was, if you see, this is one of the, there are two labs, one on the east coast of the US, one in the west coast of the US, and now they're building one in India, LIGO India. So I have only a photo because the other one is still just to be constructed. This is one of the labs here. You can see that it has two perpendicular long arms, which are 90 degrees to each other and 4 kilometers long. And you have a laser beam which is going up and down, which goes up and down almost 300 times at the time before it gets replaced by the next incoming beam. And there are some incredible things about how there are half-silvered mirrors which allow it to go up and down. But if you are not correct in the length of your 4 kilometer long chamber, and if you're off by even something like 1 millionth of a Fermi, which is the size of a proton, then your experiment is just go to the two waves, because the waves, when they go up and down, will interfere amongst themselves. That's the nature of light. It is a wave. Then they will simply cancel each other and you will be left with nothing. no laser, and no signal from the gravitational waves. So these things are aligned so incredibly, and that is the technological challenge. So I wanted to show you, this is the data which got them the Nobel Prize. These are the 3 experiments in Hanford, Livingston, and Virgo is in Italy. You can see Virgo doesn't have the sensitivity that the other 2 have. But what it says is that there is a background which keeps on coming, because this background, coming from even when I walk, there are waves being produced, and howsoever much they have been able to reduce that, it's not possible to reduce it fully. But here is a signal above the background. At the same time, this has seen a signal above the background, and you can see this also has a signal above the background. And what it says is that when 2 black holes are merging, because 2 heavy objects, gravity is always attractive, and when they come closer and closer together, at the moment when they merge, the frequency of the radiation that they emit is going to increase. So it doesn't matter what the y-axis is, the frequency. You can see in the last minutes, last seconds of this merger, so you must see it in live time, that the frequency is increasing. And in fact, for those who are curious, you can go back and hear the sound actually, which has been rendered. It's available there on the LIGO website. And you can then, from this information, you can extract out the gravitational wave, because the gravitational wave, because there are perpendicular sides. And the gravitational wave, when it goes through these laser lights, it stretches space-time itself in one direction, contracts it in the other direction, so that the 2 perpendicular parts will become momentarily different. And that difference is what is picked up by the laser lights, and this waveform is seen. So it's an incredible experiment. You can see what is the engineering challenge for this. Yeah. So these are the science goals, of course. I mean, main thing is to see what are the properties of gravitational waves. There are some more you can read through. And as I said, LIGO India is very important, because when you just have 2 machines looking up into the sky, triangulation is very hard. So the third machine will allow you to actually locate the source of that merger to a very high precision. And you can see over here that when you include LIGO India, that the localization of the event that has happened will be reduced by 100 factor of 100. That's why it's very important for LIGO India to come up. So I don't want to discuss anything more about it, but I want to highlight only one thing that I said, because the second science goal is general relativity the correct theory of gravity? Because that's the theory that predicts that there are gravitational waves. And I want to make a short aside about of what use is Einstein's theory of relativity, because I've been hearing this in the press, and I would like to just answer this. You've all heard of GPS. You have your cell phones, you your favorite taxi, and you ask to go to a certain place, and he keys in the location, and he gets you exactly there, right? And in fact, when you're picking up the vehicle, he knows when he's reached you, because his GPS tells him that he has reached there. So you know how this works. There are satellites circling the Earth. They're all some high above the ground. And because they're high above the ground, oops, sorry. I forgot that the pointer doesn't work. They're so high above the ground that the gravity there is 4 times weaker. And so Einstein's special theory, general theory of relativity says that, that because they are so far away, gravity is less, gravity is curving the space and time, and that has become less. So these clocks which are there, which keep the time in the GPS satellites, are going a little slower by about 45 microseconds every day. However, these satellites are going at very high speeds. They're going at such high speeds because they circle the Earth twice a day. And Einstein's special theory of relativity says, therefore, the clocks should go a little slower by about 7 microseconds a day. So the net result is that there is a difference in the time. The GPS satellite goes 38 microseconds a day, much faster than the clocks on the Earth. If you don't account for this correction due to relativity, then instead of reaching your location, if you calculate the 38 microseconds per day and understand that the speed of light is 30 centimeters per nanosecond, then you can immediately see that you have gone off by 10 kilometers. So from the airport, instead of coming to JLN Stadium, he would have taken me somewhere else, very, very far away, and there would have been absolutely no radio taxi available because GPS will not work. So it's not that always science discoveries are useless to people. Science discoveries can have an impact. Science discoveries can be negative, can have negative impact on society. And I think it's for human beings to determine how they're going to use the science that is discovered. But again, I want to highlight that without the science, without the technology, there will be no technology, because you do not know what it is that you have to refine. Because technology actually refines the science and implements it in a very concrete way. And the example here is that you can see that if you want a mirror to work in over a distance of 4 kilometers, then it's one of the most high precision optical instruments absolutely ever invented. And the LIGO will be able to detect the change in distance between its mirrors, as I said, of the order of 1,000th of the size of a proton, which means that it can measure the distance from here to Alpha Centauri to the width of one hair. Just imagine the kind of precision that is needed. In fact, one thing you must remember, this has happened with other experiments, particle physics accelerators as well. Since the Earth is curved, over 4 kilometers, the Earth is not flat. In fact, the Earth dips away by about almost 1 meter in the distance of 4 kilometers. So if you want to really have a flat 4-kilometer long, you must make correction for that as well. And without that, of course, you would have got no answer. So everything depends on technology. The science that you're doing is driving this technology. Otherwise, how will anyone be able to make stuff with this kind of precision? So this is the second project that I wanted to highlight. So let me just check the time because we've been a little late. I guess I'll just do this a very short kind of this thing. This is a very, very interesting project which has been on for a long time. This is the International Thermonuclear Experimental Reactor. International because no one country can do this. It's such a humongous experiment. There have been many experiments before. So what you want to do is that instead of nuclear fission, which creates a lot of waste products, which creates a lot of radioactive waste, which you need to store for very, very long amounts of time, here you have a fusion reactor. What you do is that you take heavy hydrogen, which is deuterium, heavier hydrogen, which is tritium, and you fuse it together to form helium, which is a very stable particle. And since helium is the final state, it's completely clean and green technology. You don't have all those radioactive waste products, and something that is incredible that you can do. However, in order to make this fusion happen, you must be able to actually compress your material to the size of a nucleon, of a nucleus of an atom, because otherwise these things will not overlap, these things will not interact. So the main challenge here, the technological challenge, is to squeeze this matter together. This is the plasma that you squeeze, and this plasma can be squeezed using some magnetic approaches. There's something called magnetic confinement, and it's a huge mixture of electromagnetism and hydrodynamics, which is a very, very challenging field. So right now what has happened is there are many experiments which have, so you have to give some energy to get the magnetic field to confine the plasma. The reason you need to confine the plasma is that it becomes so hot when this fusion process happens that it will simply burn down the vessel in which you are containing it. So this plasma must not touch the sides of the vessel. So to achieve that, you must magnetically confine this plasma. And what they have done is that the energy required for this magnetic field, suppose you put in some, say, 100 watts of energy, then after the fusion process, they have got back 66 watts of energy. That means they have got back around 2/3 of the energy that they have put in. So those are the experiments that have been done so far. So ITER in particular is determined to produce more energy than is put in, so that it actually becomes like a energy producing reactor, although it will not produce electricity, but they want to showcase the fact that they can actually get more energy out than they put into the system. So in fact, another goal of theirs is that although deuterium is freely available, tritium only comes from fission reactors, and part of the technology that is being driven inside ITER is also how to find and produce tritium from these reactors themselves, so that you don't need the fission technology at all, and you can be completely self-sustained. So, okay, now I go on to, so this is the kind of contributions. One thing you should understand, it's so difficult to even take this picture because this cryostat that has been manufactured in India is about 10 stories high. It's such a huge vessel, such a big engineering challenge. You can see the people are so small compared to the vessel. So this is the vessel inside which everything will happen. This is the schematic. So this is there's the RF cyclotron heating system. And these are the shields that will be there between the inner wall and outer wall. So a lot of these parts are actually being manufactured in India, although the machine itself is somewhere in the south of France. Yeah. So I come to my favorite topic, which is about neutrinos. I will just briefly tell you what the story of neutrinos is. This is something that people have asked for a long time. How does the sun shine? How do any stars shine for such a long time in such a stable fashion? And the answer to this question is that there is a combination of gravity and thermonuclear fusion. So what is gravity? Gravity is always attractive. It's something that highlighted in schools. While electromagnetism can be attractive or repulsive, there is never anything like repulsive gravity. Gravity always attracts. And so even if you have a slight amount of fluctuation in the density of the universe, that gas will come even further together because that little higher density will attract more matter towards it. And so the gravity being a long range force ultimately will squeeze this matter and squeeze this matter, and this compressed gas becomes hot, and it becomes so hot that the thermonuclear fusion processes can occur. It's a different production of helium. 4 protons simply get converted into helium, during which 2 protons get converted into 2 neutrons. And you see this friend of ours, which had not been seen before, neutrinos, come into the picture. Neutrinos are produced from the sun. These neutrinos from the sun were actually detected because the sun is so far away, and if you just say this is what is happening in the sun, you cannot see the positrons because they get annihilated with the electrons inside the sun itself. So all you will see are the neutrinos coming out. These neutrinos have been observed. I don't want to look at the details of this process. It doesn't. For those who are curious, they can look back at the slide. When they look for these neutrinos, every experiment, and there were dozens of them, found that theoretically you expected 100 neutrinos, but experimentally you either saw 30 or 40 or 50. And so there was a shortfall of neutrinos coming from the sun. And finally, they realized that the solution was that you have to look at the wave nature of these neutrinos. So this is where this particle being both a wave and this matter being both a wave and a particle duality shows up. Here we look at the neutrinos not as particles but as waves, and because of the overlap and interference of these waves, as you can see here, suppose this in the sun you started out with a combination of equal combination of red and blue. Because their masses are different, it turns out their wavelengths are different, and when you detect them in the detector, you will see a different combination of blue and red from what was produced, and that was the explanation to what was called the solar neutrino problem. And this opened up a huge field of neutrino research because it requires these neutrinos to have non-zero masses. I won't be able to tell you what the consequence of these masses is, except to highlight one thing. If you look around us, and the Hubble Space Telescope has seen so many galaxies around in the universe. No one has seen an antimatter galaxy till today. So what does that mean? If you believe that the universe began in a Big Bang, there must have been equal amount of matter and antimatter in the universe. But there are only matter galaxies around. So where did this antimatter go? Either the Big Bang is not correct and there's tremendous evidence that Big Bang is correct, or something has happened during the evolution of this universe so that the amount of matter and antimatter has evolved differently. And so this is the question that was posed even in FAIR. Is the matter property the same as the antimatter property? And this can also be probed through the neutrino sector. So this is a very large number of experiments looking into this. And this particular India-based Neutrino Observatory, or INO, is also one of these proposed experiments. In contrast to the other experiments, this is a completely indigenous experiment. You can see the last line. And it's going to be a very, very massive detector. So it'll have 3 modules of magnetized iron. So it's like a 5-story building, which is completely magnetized. And it will be in layers like this. So these layers of iron will be interspersed by some active detector, which is called the RPC. So what happens is that when the charged particle goes through this RPC, it gives a little signal, electronic signal. And so if the particle is going through this entire module, then it will give you, a signal, and then you can have tracks which you can detect, and from the detection of the tracks, you can work backwards and see what kind of interactions gave rise to it. So this is the proposal. So you can see that it's a tremendous affair because it needs 30,000 of these active detector elements, which are the RPCs, and also it needs something like 4 million channels of electronics. This is not something that is going to be built in the lab. It is actually already some 50 different MSMEs are working with INO for various parts of this construction. As I said, every portion of it is being made in India. So you can see that starting out from the 1 meter by 1 meter RPCs, we finally got to this. You can see that it's being lifted with the crane. 2 meter by 2 meter RPCs are more than 150 kilos heavy. So they are huge machines. And finally, so a lot of data was taken with those machines. This is the 2 meter by 2 meter machines. And finally, you can see that the whole thing is now being produced by industry. So the whole process has been streamlined and is now being manufactured by industry and not in labs in India anymore. So that is the whole process of the industrialization, as I said. This technology, which was not available in India, a lot of R&D was done on it, and the whole thing was transferred to industry. Same thing happened with electronics. You can see how it was started, very crude, then it got more and more refined, and now you can see that these chips are all being manufactured by industry. So they're up to industry standards. So this is a kind of work. There's those of you who I'm very far away from home, but those of you who ever go to Madurai, our IIC is in Madurai. This detector is working through the pandemic, in fact, very nicely. And a lot of students have come either during winter holidays or summer holidays to work on the machine, as you can see over here. That's the size of the RPC. Now you can appreciate how big it is. And these are all the summer students who came there and had a good time trying to understand the science and the electronics and the engineering behind these RPCs. So, okay, I don't want to talk about the science that we will do. There's a lot of science that can be done, and you can look at it later. So I want to end with two remarks. This is not yet the remark. This is just an outlook. As you can see, there are many current. Thank you, sir. Thank you. Yeah. So there are many current experiments scheduled to come up 2025, 2026, 2028, and will be working for the next 15, 20, 25, even more number of years. And they have very significant Indian participation. And INO in particular, I'm very proud of, because it's a collaboration of more than 20 research institutions and universities across India, and it's completely indigenous. And these experiments are set to probe some of the most important frontiers of physics, astrophysics, and cosmology. So I've kind of highlighted again. You can read it. I'm not going to read it again. But these are new windows. So there's some things which hadn't existed earlier. These are new windows into the origin and evolution of our universe. And each one requires a dedicated talk to do justice to its science, and in fact, another dedicated talk to do justice to its technology, which I have not been able to do. So I hope that at least it has interested you enough to go back and read more about these projects. But before I end, I want to make two final remarks. And the first remark is this: why are we interested in fundamental science? And many people have asked me this question when I have been doing outreach for the purposes of INO. And I have been thinking about it, and I have only a few things to say. For example, about 100 years ago, the electron was discovered. This discovery was simply driven by human curiosity. It had no use at all. Okay. But today, because of the electrons, we have electronics. In fact, before that, we had electricity, in fact, also magnetism. It's the same source. Electrons are also responsible for magnetism. And so the whole 20th century technology, in fact, was driven by the discovery of this electron. Okay. 1932, the positron was discovered. Again, I mean, got a Nobel Prize, fundamental science, very good. But today you have the PET scan. Right? PET scan stands for positron emission tomography, uses positrons. And I think many of you would know people or have relatives who have benefited from having a PET scan. Right? So not only PET scans, X-rays, PET scans, MRIs, all these medical imaging have actually started out being some kind of particle physics detector and have moved into medical imaging. So it's clear to me, at least, that discoveries in physics or in science in general drives development of technology. So science, engineering, and technology, I like to think as three legs of a stool without which it will just simply fall over. Okay, it just simply cannot exist. And this is something that really saddens me, because as I grow older, I find a lot of young, especially in Tamil Nadu, I don't know about Delhi, a lot of young students who want to do engineering and see no purpose or interest in physics or chemistry or no pure sciences at all. Okay, so this is something that I would really like you to understand or appreciate, that all these mega projects have tremendous scope for interaction from both public as well as students of both engineering and science to come and make a big change in the way we do science and how it will impact technology. Now, what about mathematics? It's just the last throwaway point. Okay, I think mathematics is the language of science. This is something that we don't highlight, but without mathematics, without developments in mathematics, many physics questions could not have been solved. And I think you yourselves will have many examples, but I'm going to just leave you with one. For example, this is the calculation of the Lagrange points of the sun and the earth. Okay, this is the sun, this is the earth, and you know there are 5 Lagrange points. So these are the points at which the gravitational forces of the two systems or two bodies actually cancel each other. So the James Webb Space Telescope is going to have a tight orbit around the L2 point. So it's a very important thing, because it's such a stable point. It's not a stable equilibrium, but it's a point where the force is so small that you need to give very little energy or fuel for it to be running for a very long time. And especially since you cannot refuel that machine, that that satellite, it's very important to find the place where it can last the longest time. So this is coming just from mathematics. In fact, the L1 point already has been used. The space, solar observatory is sitting at L1 point. So all these have gone into actually our understanding of geometry and the physics of our universe, and have helped us to, in fact, save money, as I say, by having the best possible position for these planets. So both science and maths are very important to understand and make advances in technology. So I have my second point. Although I said that a lot of these mega science projects are driven by technology, and therefore I think that we need to endorse them because they will also produce a lot of technology and develop a lot of indigenous technology. There is also a scientific aspect. How stars die? We know that our sun is just another star. In fact, it's just an ordinary star. And stars which are heavier than our sun, will explode into supernovae, and stars lighter than that, like our sun, will simply cool to a white dwarf. Our sun is going to die in about another 10 billion years. And stars which are much, much heavier than that will end up as black holes. However, if you look at this very beautiful periodic table, it tells you the origin of elements. And you can see that all the interesting elements, for example, I think in COVID, everyone has appreciated the need for oxygen, and the iron in the hemoglobin that carries this oxygen around our bodies, in gold and silver, are coming essentially from exploding stars. And our germanium, silicon, aluminum, all our semiconductor devices are also coming from exploding stars, which means both in the biological and the non-biological world that drives our civilization and our technology today, all these elements have actually come from the stars. Okay, without this, we are literally made of stardust. Without that, we would not be alive. In fact, without the sun, there is no photosynthesis, there is no life on Earth. But without stars, there is no iron, and absolutely, no life on Earth. So the story of neutrinos, quarks, gravitational waves is fascinating to scientists because it's driven by human curiosity. But I think that it should be fascinating for all of us because it's the story of the only universe that we will ever know, in my opinion. So I will stop there. Thank you very much. I'm sorry for the little trouble that we had.
Hello. Yeah. Thank you, Professor Indumathi, for taking us to this wonderful journey of frontiers of high energy physics. You have not only told us the research, but you also told us
जय हे भारत भाग्य विधाता।